In the previous session, we studied about how loops are dangerous. We studied how STP can resolve loops. So in this session, let's study STP terminologies and STP's operation, the working of STP. So as you can see here, these are the main terminologies related to STP. Cost, bridge roles, bridge ID and port ID. Then we have port roles, and then we come to a very important topic in spanning tree, that is election process and building of topology. And then we study about BPDUs. BPDUs are the heart and soul of STP, because it is through BPDUs everything happens in STP. And then we come to port states, and then finally topology change and convergence. So basically cost in STP is nothing but bandwidth. It's the bandwidth of your link. So we have two parameters in cost. One is known as link cost and the other called as path cost. Link cost, as I said, is nothing but the bandwidth of your of the link that you're using. Say it can be 1 gig, 100 Mbps, 10 Mbps or 10 gig, etc. So IEEE has actually defined standard metric cost for different bandwidths or data rates. And as you can see in this table, you can very clearly see that higher the bandwidth, lower is the cost metric assigned to it. So as you can see here, 1 gig is 4, 100 Mbps is 19. It makes sense because it's very logical for us to choose a higher bandwidth link over a lower bandwidth link, right? So similarly, STP prefers higher bandwidth link, and hence higher the bandwidth, lower is the cost. Then let's come to path cost. Path cost is nothing but the addition of individual link costs leading up to a router. Suppose you have to calculate the path cost to your fourth router from the root bridge. Then path cost is nothing but the addition of individual links leading up to the fourth router. So suppose your fourth router has say 3 links in between, 3 1 gig links in between. The path cost to reach the fourth router will be 4 into 3, 4 times 3, that is 12. Now let's see what bridge roles are. We have two bridge roles, and they're named as root bridge and designated bridge. What's a root bridge? As we spoke about the tree topology earlier in our session, the tree has a root. So similarly, our STP topology has a root bridge which acts as the logical center for the tree. It is through the root bridge a lot of stuff happens. It is the root bridge that controls the topology in a way, and that is why it's known as the root bridge. And the tree seems to divert from the root bridge, so that's why it's known as the root bridge. And then we have another concept known as designated bridge, whereas the designated bridge is the bridge on the least cost path which is meant to forward traffic further away from the root bridge. So as you can see in this diagram, we have 4 switches connected to each other, and suppose the first switch is the root bridge, then the others are the designated bridges. Now let's see what bridge ID and port ID is. Each and every bridge on each and every port involved in spanning tree topology has to be uniquely identified. We'll see why it has to be uniquely identified when I come to the simulation part. So what's a bridge ID? Bridge ID is a 64-bit value which consists of 2 fields basically. As you can see here, it consists of bridge priority and then the MAC address. It's basically MAC address of your interface. So the bridge priority is a 16-bit field which can contain values from 0 to 65535, and this can be controlled by the operator. He can manually edit the bridge priority. Whereas MAC is unique to each and every bridge. So this is why bridge ID together becomes a unique number, and each and every bridge in your network can be uniquely identified by these bridge IDs. The same thing also applies to port IDs, wherein you have a 16-bit value composing of port priority and port number. The port number is also unique to each and every port on a bridge. It's the physical port number of your hardware, so it's supposed to be unique for each and every bridge. And you also have this port priority which can be modified by the operator. When we do the simulations, we'll see how these two play a very important role in building of topology. Similar to the bridge roles, we have something known as port roles. We have two port roles, root port, which we usually abbreviate as RP, and the designated port, which is abbreviated as DP. So what's a root port? A root port is a port which leads you towards the root bridge. So it's a port in your topology which indicates the direction of your root bridge. That is, if you follow the root ports from all of your designated bridges, it would lead you to the root bridge. It would lead you towards the logical center of your STP topology. So that's the root bridge. So the root bridge is an indication as to how your tree is converging towards the root bridge, whereas the designated port can be thought about the opposite of root port, wherein the designated ports are actually facing away from the root bridge, so the tree seems to diverge if you move out of the designated ports. So from these uh, descriptions, you can make out that the root port and designated port are supposed to be facing each other, because the designated port on a designated bridge should eventually lead into either the root port or a blocked port. So we will be seeing in a simulation as to what ports get elected as the root port and what ports become the destination port. But however, there are two important things to be remembered here. That is, the root bridge should have only designated ports. The root bridge cannot have a root port, because that is the logical center of your topology. However, all the other designated bridges must have one and only one root port. So assuming this is our root bridge, then these, indicated by the gray arrow, become the root port. So as you can see, the root port is always the port which is facing towards the root bridge, and the green arrows indicate designated ports. Designated ports are the ones which move away from your root bridge. Now let's see what BPDUs are. BPDUs are actually bridge protocol data units. As I said before, these are the heart and soul of STP, because it is only through BPDUs STP will be able to transmit all its information. It will be able to converge into a tree. So let's see what BPDUs are meant for. The STP operates on the principle that all bridges, including the root, have to advertise their current understanding of the network through their BPDUs. So this is done by sending out configuration messages encoded into the BPDUs. What happens is all switches listen to these configuration messages. They listen to these BPDUs sent out from each and every switch in the network, and they compare the information that they get from the neighboring BPDUs to the information that they have internally. Once they do this matching, then whoever so supposed to have the least bridge ID, or whoever lays a claim to having the best BPDU, elects himself to be the root bridge. So we'll see all that. We'll see all how it happens in the simulation. And BPDUs are exchanged regularly every 2 seconds by default. So this is something known as hello timer. So I'll also be explaining the timers when I come to the BPDU frame format in the next slide. And another important thing to remember about BPDUs is that BPDUs are transmitted between switches by the switch putting its own MAC address as the source, and it uses a special STP multicast address which is defined by this value that you can see here, 180C2000000. This is the standard STP multicast address. So basically BPDUs can be set as multicast messages having multicast address of STP, which is this number right here. Now let's look at the BPDU frame format. So as you can see, this contains a lot of information about the bridge. This contains a lot of information which we have previously studied, like the bridge identifiers. We studied port identifiers, and then as I was talking in the previous slide, we have a few timers like message age, max age, hello timer, and forward delay. So I'll be talking about these stuff when I come to port states and when I come to explaining how the topology is built. But for now, let's concentrate on the BPDU type for now. If the BPDU type indicates or it has a 0 value written into it, then it's a configuration BPDUs. Configuration BPDUs, as we discussed before, are sent out when the network is to be when a root bridge is to be elected, or when the network is to be configured. So that's known as configuration BPDUs. But if the BPDU type is set to 1, which indicates a topology change notification, and then we have something known as flags as well, where bit 0 is the topology change, and if the bit is set, then it's a topology change acknowledge. So in our last terminology related to STP, we'll see what topology change notification is. Now let's come to another important terminology involved in STP, and these are called as port states. Port states are nothing but the different states which a port on a particular bridge goes through during the election and topology change process. So as we can see, we have 5 different port states: disabled, listening, learning, forwarding, and blocking. Basically, disabled is not a part of STP topology, STP port states. It's a very generic port state, wherein the operator would have probably manually shut down the port, or if you encounter a fiber break or a link event, then your port goes to the disabled state. Now let's see what the listening state is. Listening is a state wherein your port is listening to configuration messages from the network in order to make a decision whether it has to go forward into the next step, which is learning, or if it has to go back and into the blocking state. So during the listening state, as you can see in the tabular column here, this clearly tells you how BPDUs are handled when compared to data frames. It's important to realize that BPDUs are to be given priority, because it is only through BPDUs that we get to know of the network. It is through BPDUs we get to know of the faults in the network. So BPDUs are handled in a different way when compared to data frames. So during these stages of the ports, we are not supposed to transmit any data, right? So learning is that stage wherein you're still listening to configuration messages in order to make a decision. And then we move into the third state known as learning. So learning is a very important state wherein you actually do receive BPDUs, and you do transmit BPDUs as well. But the important thing that happens in learning is it still doesn't go into the forwarding mode. So it's only in the forwarding mode where you start transmitting data frames. So in the learning mode, you're still not forwarding any frames, but you have populated your address tables. You have learned addresses and you're populating your address table. So that's why it's known as the learning stage. And then we come to the forwarding state. In the forwarding state, this is the probably the last state in STP wherein you can say that it's in the normal operating mode, because forwarding state is the state of the port where it transmits and receives both BPDUs and data frames. So it's a normal operating state of any port you see on the switch. Now what's a blocking state? This is a very important state, because a blocking port is the one which prevents loops. So blocking port is the one which is supposed to be the port which is going to lead you into a loop. So that port is supposed to be blocked. So the important thing to know about a blocking port is that it is different to being in a disabled state, because the blocking port also does receive BPDUs. As I said before, it is important for the blocking port to get enabled, because STP offers us redundancy, right? As we learned before, it offers us redundancy as well. If the main link goes down, then it is the job of the blocking port to push himself into the forwarding state so that an alternate path gets enabled. So hence the BPDUs are still being received even though your port is in the blocking state, sorry. Now let's go through the state machine chart that we have here. So this shows that initially ports start off from the blocking state, and they listen to configuration messages, they listen to these BPDUs, and they go into the listening state where they start listening to these BPDUs, and they have a timer known as forward timer. So forward timer usually in STP is set to 15 seconds. So when you're in the listening state, if you feel that things are fine, and once the forward timer expires, you jump to the learning state where you start learning addresses. But if you feel that you're not supposed to go forward, if the port is not supposed to go into a forwarding mode, then BPDUs would indicate you to go back to the blocking mode. So that's what this arrow mark here is indicating. So the listening state would go back to the blocking state, or if things are fine, then you would go from the listening state to learning state. Now again, even in the learning states, if BPDUs indicate to you a problem stating that you're supposed to be in the blocking state, suppose you are the port that is going to cause a loop, then the learning state would also go directly back to the blocking state. But if things are looking fine, and again the forward timer expires, which is another 15 seconds, the port would jump from learning to forwarding state. So as we said, forwarding is a normal operating state of the port wherein it transmits and receives data frames, it transmits and receives BPDUs as well. So the port finally comes into the forwarding state. Now again, if the BPDUs indicate that there is a fiber break elsewhere and you're supposed to or there is a loop created elsewhere and this port is supposed to go into blocking state, even when you're in the forwarding state, once the BPDUs indicate to you, you go back to the blocking state. So this is how BPDU plays an important role in STP. So we've looked at the different terminologies of STP. So in the next section, I'll be covering the root bridge election and how STP builds its topology with a small simulation. And also we'll be seeing what happens when the topology gets broken and how topology change notifications are sent and how the spanning tree reconverges itself. And we'll be ending with the limitations and conclusion.